In this problem, a person is holding a heavy kettlebell at rest and their arm is making an angle of 45 degrees from the horizontal. We're asked to find the force that the deltoid muscle is applying in order to keep this system here at rest. The main ideas involved in this problem are identifying all the forces and torques that are present in this situation and understanding static equilibrium and the conditions that requires, namely that the sum of all torques and the sum of all forces are both equal to 0. The first step in this problem is identifying all the forces that are present and determining where they are acting. The first force is the force from the shoulder, which is not shown in the initial diagram. The pivot point in this problem is the shoulder, and the force that the shoulder is applying is acting in some direction, but is applied at the pivot. The second force is the force that the deltoid muscle is applying. This force acts in the purely horizontal direction and is a distance of 10 centimeters away from the pivot. The third force is the force of gravity acting on the arm, which is applied at the arm's center of mass, which is a distance of L/2 away from the pivot point. And finally, there's the force of gravity on the kettlebell, which acts vertically down and is a distance of L away from the pivot. The next step is to sum all of the torques that are present in this situation here. The forces that supply a torque are the deltoid force, the force of gravity on the arm, and the force of gravity on the kettlebell. The shoulder force does not apply a torque because it's acting at the pivot point. So, the three torques that are present are the torque from the deltoid force and the two torques from gravity acting on the arm and the kettlebell. The torque from the deltoid force produces a rotation in the counterclockwise direction. We know this if we perform the cross product between r, the vector going from the pivot point to where the deltoid force acts, and the deltoid force, which acts in the horizontal direction. Because this rotation is in the counterclockwise direction, the torque is considered positive by convention. The torques produced by gravity produce a rotation in the clockwise direction. Again, we know this if we perform the cross product between a vector going from the pivot to where the gravity force is applied and the gravity force which acts vertically down. Performing this cross product, we see that the rotation is in the clockwise direction, which by convention means the torques are negative. We can then solve this expression for the torque produced by the deltoid muscle and can rewrite the torques in terms of the forces and the distance vectors that cause them. Doing so, we see that we have the force of the deltoid, which we're trying to solve for, times the distance from the pivot that force is applied, times sine of pi minus theta. Because when we perform the cross product, we multiply this term here by sine of the angle between the vector r and the deltoid force, which in this case is this angle. So, for the argument of sine, we need pi degrees minus this theta degrees that we're told in the problem statement. For the torques produced by the gravity acting on the arm and the kettlebell, we have, for the arm, the mass of the arm times the acceleration due to gravity times L/2, which is the distance from the pivot point that the gravity force on the arm is acting, times sine of pi/2 plus theta. Again, when we perform the cross product between r and fg, we want to multiply fg times r by sine of this angle here. In this case, the angle is the angle theta, which we're told in the problem statement, plus the 90 degrees to get to fg. The same thing is true for when we find the torque produced by the kettlebell. In this case, we have the mass of the kettlebell times the acceleration due to gravity times the distance L from the pivot where that force is acting times again sine of this total angle here. The final step is to solve the equation we just derived for the deltoid force, and when we do so, we arrive at this big equation here. We then plug in the numbers that we are given in the problem statement and evaluate to find that the force applied by the deltoid muscle is 882.9 newtons.